In this video, I want to talk about the unique representation theorem and define what coordinate vectors are. Okay, so let me begin with some context. So V is some vector space that has a basis B with vectors B1 up until Bn in it. Our goal is I'd like a way to describe my vector space using those basis vectors. Okay, so the unique representation theorem says the following. It says that each vector x that's in my vector space V can be written as a linear combination in the form x equals c1 times b1 plus c2 times b2 plus ... plus cn times bn. So it's a linear combination of the basis vectors, and that should be doable in a unique way. So the reason for this, the reason why x can be written as a linear combination in the first place, actually, no, let's put that in red. The reason why it can be written as a linear combination in the first place is, well, it's because the basis has the property that it spans whatever set we're talking about, in this case, V. So this is by the spanning property of a basis. And the fact that it can be written in a unique way means there's exactly one choice of what C1, C2, and Cn are. And that's coming from the fact that a basis is linearly independent. And we've seen that in the context of Rn before. When we were talking about vectors in Rn, if they were linearly independent, the equation Ax equals B would, if it had a solution, that solution would be unique because there's no free variables when our vectors are linearly independent. Okay, so now I want to introduce some notation and define a term. So these weights, C1, C2, all the way up until Cn, if we write them as a vector, so if I write C1, C2, ... up until Cn as a vector, this is called the coordinate vector of x relative to my basis B. And the notation for this is I put the vector x in a bracket, and then as a subscript I write B, my basis. And I say that, oh, this is the coordinate vector of x relative to the basis B. And the coordinate vector is just the vector where I write all of those weights as the entries. So C1 up until Cn, they are sometimes called the coordinates of x relative to B. Okay, so let's do an example to get more familiar with what is this notation saying. So it's really common to denote the standard basis as script E. So this little notation here is this is a script E. Script E. Okay, so E1, E2, E3, I'm going to let that be the standard basis for R3, and x is the vector 2, -5, 3. I want to find the coordinate vector of x relative to the standard basis. Okay, so what does that mean? Well, what that means is we're trying to write our vector 2, -5, 3. We're trying to write it as a linear combination of these basis vectors. I'm going to try to write it as, some number C1 times E1, which is 1, 0, 0, plus some number C2 times E2, which is 0, 1, 0, plus some number C3 times E3, which is 0, 0, 1. Okay, so this is what we're trying to do. But these basis vectors are simple enough where we could probably see what C1, C2, and C3 are just by looking at it. So C1, just by looking at it, this has to be 2. C2 has to be -5. And then the C3 has to be 3. If I want to make this linear combination be 2, -5, 3 after I add everything up. Okay, so my coordinate vector, so x, let's write my notation for the coordinate vector, brackets around it, and then I write the basis in the subscript. So the basis, we're calling it script E for the standard basis, is a vector that I get when I put these weights as the entry. So I put 2 first, and then -5 after that, and then 3 after that. So notice that that's actually the same thing as the vector that I started with, 2, -5, 3. And it turns out that is always going to be the case when we talk about the standard basis. So in the standard basis, script E, it's always going to be the case that the coordinate vector of x relative to the standard basis is just going to be the same thing as x. When we talk about other bases, so not just the standard basis, this won't necessarily be the case. So it's really rare for the coordinate vector just to be equal to x. It only happens with the standard basis. Okay, so let's do another example where we have a different basis, not just the standard basis. So let's say that my basis has these two vectors, 2, 3, and then the second vector is -1, 1. Turns out this is a basis for R2. So part A of this example is, if my coordinate vector, so this time I'm given my coordinate vector, instead of trying to find it, if my coordinate vector equals 1, 4, then what's x? So again, I really want to break down the definition. So x is a linear combination of my basis vectors, where the weights are the entries of this coordinate vector. So it's the first entry, 1, times the first vector in the basis, 2, 3, plus the second entry of the coordinate vector, 4. So again, the 1 and this 4, they're the weights of my linear combination. And then the vectors that are in the linear combination are the basis vectors. So 4 is multiplying b2, which is -1, 1. And if we work out what this is, we get -2, 7. -2, let's write that -2 a little bit better. -2. So what I want to do next is I want to describe geometrically what this coordinate vector 1, 4 represents. Okay, so if I have my x, y axes, what I'm going to do is I'm going to draw in these basis vectors, b1 and b2, on my xy plane. So b1 maybe looks something like this. It goes 2 in the x direction, 3 in the y direction. So the slope is a little bit more than 1, so that's b1. Let's put b2 in green. So b2 goes a -1 in the x direction, and then +1 in the y direction. So maybe something like this. Okay, and now what I'm going to do is I'm going to start to draw like a coordinate system, but thinking about one direction being in the direction of b1, and then one direction being in the direction of b2. But I think as I start to draw it, it'll make more sense what I mean by this. Okay, so I'm going to start to draw some lines. I'm going to start to draw a line that's parallel to b1, just going through where b1 is. And then let's draw a line through where b2 is. So here's where b2 is. And then what I'm going to do is, I'm going to sort of do the equivalent of drawing tick marks on each of these new axes. So here's sort of like 1 unit along this axis. 2 units would be doubling that length. So here's where 2 units would be. So -1 would be, the opposite, would be on this side. And then on the other axis, so here's sort of going 1 unit in this direction. Going 2 units would be doubling this vector's length. So 2 units, 3 units would be tripling it, 4 units would be quadrupling it. And then I could go in the opposite direction as well, like I could go -1 units. So I'm going to start to make a grid here, but it's going to be a diagonal grid. Okay, so I'm going to make a line through this sort of 1 unit in this direction. I make a line here. And notice that I'm drawing these lines parallel to this line that I draw this green vector along. So I'll draw a grid here. And then I'll do the same thing through this green dots. Let me draw lines that are parallel. Oh, imagine that's parallel. Another line here that's parallel to that blue vector. Another line here that's parallel to that blue vector. Another line here that's parallel to that blue vector. One more here. So notice that I'm creating this other grid. This is a coordinate system that I'm creating. So now, when we talk about our coordinate vector, which is 1, 4, what that means is sort of go 1 unit in the direction of the first basis vector. So go 1 unit in this blue direction. So that just takes us to this dot. And then the 4 means we'll go 4 in the direction of the second basis vector. So that was this green vector. So here's 1 unit in that direction. Here's 2 units in that direction. Then 3 units in that direction, and then 4 units in that direction. So we'd be going all the way until here. So that's what the 4 sort of represents. And then what it means to do is, well, then add those two together. add the blue one and that gray one now together. And if I were to do that, I would get this red vector right here, because I'd be sort of drawing in the diagonal of this parallelogram. So this resulting vector is the vector x that we got. So x ended up being -2, 7. So this is how we visualize what a coordinate vector is. This notion of coordinate vectors, depending on my basis, actually implicitly defines a coordinate system like this. Okay, so let's do another part to this example. So what if this time I'm given my vector x, and it's -2, 27, and I want to find the coordinate vector associated with it. So to do that, what I need to do is I need to write my vector -2, let's put the negative closer to the 2, -2, 27, as a linear combination of my basis vectors. So I got to write it as c1 times the first basis vector plus c2 times the next basis vector, -1, 1. And then I have to solve this system. But to solve this, I form an augmented matrix. And that we have done a bunch. We have set up augmented matrices and row reduced them to solve them a bunch. So I've actually gone ahead and done those row reduction steps for us to save some time so I can talk about the concepts a little bit more. Okay, so now that this is row reduced, let's go ahead and write down the equation for each row. So for the first row, I would write C1 equals 5. Notice I'm calling it C1 as opposed to X1 because I call this weight C1. And there's one thing that I forgot to mention, which is, so this coordinate vector x, b, this is going to be the vector that I get when I find these two weights, C1 and C2, and I write them as a vector. So that's ultimately what I want to get. So from the first row here, I get that C1 equals 5. From the second row, we get C2 equals 12. And at this point, I can write down my coordinate vector. So x, the coordinate vector of that for the basis b, is the vector 5, 12. So equations like this, when I try to write my vector as a linear combination of my basis vectors, we can rewrite this equation in matrix form. So I want to end this video by talking about that and what that looks like more generally. So in general, if I try to write my vector x as a linear combination of the basis vectors, b1 up until bn, we'll get some linear combination. I've just said the weights are c1 up until cn. And then we can rewrite this in matrix form. So I can put the column vectors b1 up until bn as the columns in some matrix. And that's going to get multiplied by the vector that has c1 up until cn, those weights, as the entries of the vector. So this matrix b1 up until bn that has the basis vectors in it, this is called pb, or p subscript b. And notice that this vector right here that has c1 up until cn in it, well, that's just my coordinate vector. That's the coordinate vector of x relative to this basis b. And whoops, I noticed that I forgot to write my vector notation there. Okay, so this matrix PB has a special name. This is called the change of coordinates matrix. Change of coordinates matrix from B, whatever my basis is, to script E to the standard basis. And the reason for that, the reason why it's called the change of coordinates matrix from B to E is, notice what it does. It multiplies a coordinate vector, so it multiplies a representation of x in terms of the B coordinates. And what it outputs is, well, it outputs the vector x. And that's how I represent my vector in terms of the standard basis. So that's why this changes the coordinates from B to E. Okay. So notice that the matrix P, B, this change of coordinates matrix, this is invertible. This matrix is invertible. And it's invertible because the columns of this matrix are a basis. And because those columns form a basis, it means there's going to be a pivot in every single column and every single row. Okay, but because my matrix is invertible, we could multiply both sides by the inverse if we wanted to. And if we did that, we would get P B inverse times x. And on the right-hand side, we would just get the coordinate vector, x, b. So if I knew the inverse of this change of coordinates matrix, I could use that to quickly figure out my coordinate vector. So this matrix right here, what it's doing is it's multiplying a vector x, where the coordinates are in terms of the standard basis. And what it's outputting is a coordinate vector in terms of the basis b. So it's outputting the coordinate vector. So this is also a change of coordinates matrix. But it reverses the direction. Change of coordinates, oops, sorry, I forgot to write matrix. Matrix from E, so that's the standard basis, to B, whatever our basis is, that's a given. So in the next video, we'll talk about how do we apply this concept of coordinate vectors to other vector spaces. So not just Rn, but say, for example, Pn, polynomials, or other more arbitrary vector spaces.